Hello, awesome people. Today we're getting to start a completely new topic, which is waves. What is a wave? Well, let's take this charging cord as an example. And you can see if I jiggle this side, this causes the cord to bounce. And what we're looking at here are waves that are bouncing between one hand and the other. I'm holding this one fixed, so this is kind of a reflecting boundary condition. I can get the waves to be standing waves. I can get the waves to be kind of weird waves. So depending on how I shake this wave, this hand, I can get completely different behaviors for my waves. So this is precisely the process that we're going to study. But there is one very important difference between what we did before until now and what we're going to do from now on. Before, we have been looking at an oscillation at a particular point. So that if we were to, for instance, plot the theta position of a pendulum as a function of time, we would get something like this. But it was all measured at one place where the pendulum was. So when we looked at waves previously, we looked at something like that. d theta dt squared is equal to f of theta and t. And that was an ordinary differential equation. There was only one independent variable. Okay, that was t. Everything else depended on t. There could be many dependent variables, theta, omega, but all as a function of only one independent variable, t. So now that's all changing because now we have a wave that can propagate in space. So in addition to time, we also have space, t and x. That will be two independent variables. So let's make this before. And this is now. And we are considering waves, and this is going to be part 1 of lecture 10. So now we're going to consider equations of motion, for instance, that look like that, and we're going to talk about these kind of weird curly derivatives. So the second derivative of y with time will be given by the second derivative of y with space times the speed of the waves, as we will see in a second, but for now it's just a constant that is stuck in here. And so you see here that y, which is going to be the vertical displacement of the string through which we're sending the waves, is our dependent variable. And t and x are independent variables. All right, so dependent, independent. And so because there are more than one independent variables, that means that we're dealing with a PDE, a partial differential equation. And that's what we're going to be solving. Perhaps you heard about that and they sounded scary, but we will demystify them right here and now. So let us focus on the case of a string. Okay, so our string has mass, so the more of a string we consider, the more mass it will contain. And so delta m of a piece of string of length delta x will weigh mu times delta x, where mu is mass per length. Okay. So now let us write down equation of motion for a little piece of a string. So for that we can draw a diagram. So that will be y, that will be x, and then there will be a string that might look like something like that. Okay, we are going to have a few positions at which we're going to be keeping track of what this string is doing. This will be position yi. This will be position yi minus 1, and that will be position yi plus 1. All right, so these are going to be the dividing lines between these positions. Over here, over here, over there. And in order to model the behavior of this piece of the string right here, so our string kind of goes all the way. Let me just make it thicker so that it's clear that it has some weight to it per unit length. So to model this piece of the string, we will need to write out equations of motion. And equations of motion here are that there is a force that's acting, that's the tension force, that's acting along the string in this direction. And there is also the tension force that's acting along the string in this direction. So what will be the equations of motion of the string if it can only move in one dimension, up or down? And we also will assume that the displacements of this string is small. So we're going to assume that yi is small. All right, so then what that means is that the angle that the string makes with respect to the x direction is tiny. So what we're trying to say here is that we are going to be able to use small angle approximation. So let's write out what will be the acceleration of this string in the vertical direction. So we're going to write out that delta m, the mass of this element associated with our coordinate y, times the acceleration, the second derivative of yi with respect to time, is going to be equal to the sum of all the forces projected along the y direction, right? So there will be t y over here minus t y over there, and we can write them in the following way: yi plus 1 minus yi divided by delta x, where delta x is going to be this and that, and also that. So this is the slope of this string with respect to the x-axis. So this is the slope that the string makes with respect to the x direction right here. And t times that slope gives us the y component of the force. So if we multiply all of that by the tension of the string, then this times that will give us the force in the y direction on the right side of our mass element. Then we need to subtract from that the force of tension, pulling the string to the left and, in this case, down. So that will be yi minus 1 divided by delta x. And all of that is multiplied by t. So this is t times the sine of the angle that the string makes minus t times the sine angle that the string makes on the other side. And because the angles are small, we can replace the sine with just the slope. So this is the equation of motion for this little piece of the string. And we can rewrite this by reshuffling things around. So how would we do that? Well, let's express what this second derivative is with respect to time. And that will be equal to t over here divided by delta m, and delta m is mu times delta x. And there is another delta x from here, so there will be a delta x to the second power. And if we were to add these all up, we're going to get yi plus 1 minus 2yi plus yi minus 1. Or, in other words, you might have actually seen this expression. It's a second derivative of y with respect to x. This is t divided by mu times d2y dx squared. So we have just derived the PDE that describes propagation of waves through the string. And if we were to denote this prefactor as c squared, we will have obtained the equation in exact same form as we wrote it to begin with, where c, as we will see in a second, will actually be the speed with which the waves can propagate through the string. And we actually can write down the solution to this equation, to this wave equation, in the following way. Y is going to be equal to f x plus minus c times t. So both of them, with the plus and with the minus, will be solutions. X with the plus is a wave that propagates to the left, and x with the minus is a wave that propagates to the right at the speed c, plus sum of any number of waves is also a solution, which is pretty spectacular. And that's because this is a linear equation. So two solutions added together, subtracted from each other, or added together with coefficients will always give you a solution. That's the beauty of the linear system. So this looks pretty good. So the right-hand side here, this one, is already written in a very convenient form for numerics, because we've already discretized the second derivative. And in case it wasn't clear why this is second derivative, well, see, it's a difference between two first derivatives. Divided by delta x, so it's a discretization of the second derivative, which is what the second derivative is, the derivative of the first derivative. So now let's take a look at the time dependence. So let's discretize this term. So this term will look like that. d2y dt squared is going to be discretized in exactly the same way as we did for the spatial derivative. So it will be yn plus 1 minus 2yn plus yn minus 1 divided by delta t squared. And let's get our notation straight. We are going to put in I indices at the bottom to denote the spatial position, and we're going to put the n indices at the top to denote the temporal position. So this is time, and that is space. Okay? So let us now write out what this is equal to from here. This will be equal to c squared times a yi plus 1 minus 2yi plus yi minus 1. And of course I wrote this here, but it shouldn't be here because everything is at the previous time, and this will be divided by delta x squared. So this is what we have, except now we specify that all of these are at the previous time. So we have now gotten a discrete equation where knowing values at the current time and the previous time leaves us with only one unknown, which is the value at the next time, at the n plus first time. So that will be our algorithm. That's precisely what we're going to do. On the next slide, we're going to write out what is the expression for yi at n plus first time. And that will give us our numerical scheme that we're going to play around with, both now and in the assignment that you already have. I'm going to see you in part 2 of lecture 10, where we're going to do all that, and we also are going to check that indeed these are actually the solutions to our wave equations. So lots of excitement to come. I'm going to see you right there. Hello and welcome to part 2 of our exciting lecture 10, where we're continuing to discuss waves. And in particular, right over here, we have obtained a discretization of our wave equation. And all we need to do is to just solve for that one unknown, yin plus 1, the value of displacement of our string at the new time, at the position I. And then we're all done, because if we know the string at the previous time and in the one before, we're going to know what it is at the next time. So let's write out what the solution is. So yin plus 1 is equal to c squared times delta t squared divided by delta x squared times, here we're going to write out yi plus 1 minus 2yi plus yi minus 1. All of this at the nth time step. And all that's left over is 2yin minus yin minus 1. So that's it. We have found the value at the next time step of our displacement of the string. And for convenience, this piece is typically denoted as r squared. So we can simplify this just a little bit. So what we can do is we can combine this term with that term. And what we're going to write down as a result is that the solution at the current point in the next time, yin plus 1, is equal to that minus that, so it will be 2, 1 minus r squared times yin plus r squared times yi plus 1n plus I minus 1n minus yi n minus 1. So what you see is that the new value at the new time is given by the values at the current time, at the current point, at the 2 points surrounding that point, and also the value at the current point at the previous time. So that is kind of the picture of what's going on, where we have time going up, space going to the right. This is I minus 1, this is I plus 1, and this is I. And this is n plus 1, and that is n minus 1. So what we're doing is we're saying that this value depends on this value over here, these two values over on the sides, and that one value over down there. So this cross that's made up of all of these points is called a stencil. And so you can see that this point over here is going to be expressed in terms of those points over there. This one, these two, and that one below. So that is how our numerical scheme is able to take the solution at the current time, at the previous time, which we both know, and go and figure out what's at the next time for all the points, and then apply the same algorithm again and again and again, and advance the solution forward in time. So, knowing prior history at n and n minus 1 can move forward with the calculation. That is fantastic. So how are we going to solve this equation? Well, we will need to give it some initial and boundary conditions. And for that, we will first initialize. So we're going to set yi at n equals to 0 and yi at n equals to 1. And then from this, we will get y I at n plus 2. Okay, so we set this one, that one, and we get that one. All right, hopefully that makes sense. And then we can keep on going and going into the future, all the way out as far as we need to go in time. So what we're going to do now is we're going to discuss more the partial derivatives. We're going to see how to find solutions to these equations. We're going to discuss the boundary conditions that we have so far ignored. And we're going to discuss a little bit of the stability of the spring. Plus, we're going to talk about a realistic strain. And we're going to see what that means. So let's talk about the partial derivatives. You might have noticed that that was this really weird kind of D, but Greek delta rather than Latin D. And so what the partial derivative actually does is, if you have a function, a y of tx, then when you compute dy dt, then that is y of t plus delta t x minus y tx, all of that divided by delta t. The same way we can define the spatial derivative, where dy d partial x is going to be y of t evaluated at x plus delta x minus y of tx divided by delta x. So these are the partial derivatives. Now that we are armed with the definition of partial derivatives, we can move on and figure out how to find solutions to these partial differential equations. But before we move on, let's just reiterate. So what is dy dt? We just changed the time and left everyone else the same. So x stayed the same. The only thing that changed was the time. So we're seeing how our function of two arguments, t and x, changes in the t direction. That's why it's called a partial derivative. Only one change is happening at a time. T is changing. dy dx is the same physically. It's just what we're looking at here is the change of our function only in the x direction. So we've added delta x to x, and that gives us the partial derivative of y, because we evaluated y at x plus delta x and subtracted from it the original value. So we're only looking at the change of y in the x direction. So this is what the physical meaning of a partial derivative is. And so let's take a look at the let's take a look at the solutions. To our PD. So as we see on the left, our PDE is rather simple. So let's try and check whether that solution that we wrote down is actually a solution. So that's the claim to fame, that the solution to this PDE is any function f that's smooth, so that we can difference it, of an argument in the form x minus ct, where c is a constant. That's the speed of our wave, as we will see in just a second. So let's check if this is indeed the case. So we are going to compute what dy dt is, and that will be dy dt is going to be minus c times f prime. And what is d2y dt? The second derivative of y with respect to time, or the derivative of the derivative of y, that will be minus c squared times f double prime. And here f prime and f double prime corresponds to the derivative of f with respect to the entire argument. F of blah, so this f prime is df d blah. Okay, where blah is this argument x minus ct, taken as a single variable. So let's do the same thing for difference of y with respect to x. Let's go over here and do that. dy dx is going to be simply f prime, because x doesn't have any prefactor. And dy d2y dx squared. My hands refuse to write, as you can clearly witness. d2y dx squared is going to be equal to just f double prime, for the same reason. So now we can combine these expressions, this one and that one, together and check whether the result will be a solution. So let's try and see if that's the case. So d2y dt squared is equal to minus c squared times f double prime. That is supposed to be equal, I will put a question mark, to d2y dx squared times c squared, right? That's our equation. And so let's check if that's indeed going to be the case. So we're going to multiply by c squared that expression, and that is f double prime. And you can see that this one and that one, they are indeed equal. So check, this is indeed a solution. In fact, what you will see is that a wave that propagates backwards, so where c is negative, will also be a solution. So what typically people write is that plus minus c in this solution indicates the waves that are propagating to the left and to the right, assuming that c is positive. So both g of x plus ct and f of x minus ct are solutions. So any solution which is going to be any expression that is going to be the sum of these two functions will be also a solution, because it's a linear equation. So for instance, the sum of these two, let's call it h, will also be a solution for any functions g and f which are differentiable. So what we have just done, we have found a general solution for our partial differential equation, and therefore we have just accomplished this task, find the solutions. The next one we're going to move over is the discussion of the boundary conditions, stability, and we're going to discuss what we mean by a realistic string. Stay tuned, that is all coming in the next part of this lecture, part 3 of lecture 10, and I'm going to see you there. Hello and welcome to part 3 of lecture 10, where we're going to start with the discussion of the boundary conditions. So what is a boundary condition? Well, if we have a string like that with two ends that we will denote with y0 and yn. N is a bad number because it's used for time, so let's denote it with yi max. So if we have such a string, then we are going to be setting these two values to something physical to represent the fact that these two ends are either fixed or free or they're shaken around. So that will often involve the nearby values of our discretized string, displacements of them. And so that will be y1 and yi max minus 1. So suppose that we would like to fix both ends such that don't move anywhere. That means that y0 and yi max are constant. So in this case of fixed boundary conditions, we're going to say that y0 and yi max are zeros. They don't move anywhere. But now there could be also another situation when we would like to let the ends move up and down freely. So in this case, they're not going to be fixed, and they're going to be able to do whatever they want. And that is called the free boundary conditions. And in this case, in order to let them move, that means we don't apply any force. And remember that the force was proportional to the derivative, y1 minus y0 divided by delta x. So if we want the force to vanish at the boundary, we would set y0 to be equal to y1. So these are going to be the boundary conditions. Then similarly, we will set yi max to be equal to yi max minus 1. So that is a free boundary condition. Finally, we're going to consider periodic boundary conditions. So what is periodic boundary condition? That is, if a wave comes out on the right, it will come back on the left. So that means that when this one goes up, this one will go up as well, so as we prepare the left-hand side for the re-entry of the wave. So that means that y0 is equal to yi max minus 1. So hopefully that makes sense. That's a lot of physics, so please let me know if you have any questions by submitting the quiz. Then I will be able to respond to these either in another video or during a quick chunk of office hours, or just direct it to you. Okay, so now we're coming to the next topic of stability of our scheme. So we would like to know whether the scheme is actually going to blow up in our face or not. And here is where it's useful to draw a diagram. So this is going to be time. This is going to be space, that's x. And at our t equal to n minus 1, we are going to have a solution. At t equal to tn, we are also going to have a solution. And we will strive to find the solution at tn plus 1. So how are we going to do that? Remember, for that we are going to use our stencil. So if we are interested in a value at this point will depend on all of those other 1, 2, 3, 4 points, 3 at the current time and 1 at the previous time. And so each of these are our time steps, dt. And we would like to understand when will our scheme be stable. And the condition for stability turns out is what sets the time step. In fact, the condition is that delta t is no larger than delta x divided by c. That's the Courant condition. We can take the time step that is limited by this condition, because if we were to take too long of a time step, then we would need to know the conditions at those other faraway cells, because the waves would have had a chance to reach there. And so what we want to make sure is that the waves from outside of our stencil are not getting to the point where we are getting the solution, because otherwise we wouldn't have all the information that's necessary to reconstruct the solution there. So what it means is that if we were to send the waves left and right, they would need to enclose our solution point over here, such that no information from outside will have a chance to get inside of this triangle. And so because the equation for the wave is that x is equal to ct, then it means that delta x is equal to c delta t. And we know that we would like to have this condition, that delta x is greater than c delta t, so that the waves from outside can get inside. And so that is literally what's giving us the Courant condition over here, that delta t is less than delta x over c. So that is a really fundamental constraint, that any explicit method that computes directly the value in the future based on the values currently and in the past. There are implicit methods that allow us to relax this. We will not be touching that. Happy to talk about this one-on-one or during the office hours if you're interested. Finally, let us discuss what we mean by a realistic strain. Let's call it more realistic strain. Well, this is a strain that has some stiffness to it, and we will introduce stiffness and denote it as a parameter epsilon. So we will be able to incorporate the stiffness in our equations by adding an extra term that is responsible for the extra energy that the spring will be able to carry due to the stiffness because of the stretching. So that will be d2y dt squared is equal to the speed squared of our waves, d2y dx squared, minus this dimensionless stiffness Yes, it is a fourth order partial derivative, and that, it turns out, how stiffness enters into the equations of motion. If you're interested, read the footnote number 14 on page 170 in the textbook. That explains to you somewhat quantitatively, or maybe not too quantitatively, more qualitatively, where the fourth order derivative originates from. But for the purposes of our problem set, all we need to do is to add this extra term with the fourth derivative and see what happens. So there is, of course, a complication over here, that we now have a fourth derivative, and we will discretize it, no problem, as a difference of two second order derivatives. But that means that we will have to add 2 boundary cells instead of 1. That's not really a problem because for the solution, for the assignment, what I'm suggesting that you do is you apply periodic boundary conditions. So you're going to borrow these 2 cells on the right from the 2 cells on the left. So it will be the same thing as the periodic boundary condition where we set y0 to be equal to yi max and yi max to be, sorry, y0 equal to yi max minus 1 and yi max to be equal to y1, right? What we're going to do is we're going to do the same thing but for 2 cells. So y0 and y1 will be equal to the last 2 active cells, which will be yi minus I max minus 2 and yi max minus 3. And the same thing for these 2 cells as well. So thanks a lot for watching. I'm going to see you in lecture 11, where we're going to be talking about random walks and diffusion. I hope you had a lot of fun here, and you're going to have a lot more fun in the next lecture. See you. Bye-bye.